All right, welcome to a new day. Let's keep talking about pointers in memory. So we learned a lot about pointers last time. We understand now how to make very weird arrangements of memory like this. And I just want to start us off with a question. So 2 questions for you. We know that the star is disgustingly overloaded. It means multiplication before last lecture. If you say star in a variable's type, what does that mean? So like I say, it's the part of a type, right? Like int star p, blah, 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 and equals dot, dot, dot. What does that one mean? And then if you use star somewhere other than a type, what does that one mean? So that's this kind of thing, like star p equals star p plus 1. So both uses of the star there. What do those mean? What's the difference? All right, remember their names? So, all right, the first one is creating the variable, right? So int star p, that creates a pointer. That one makes a pointer to something. So that one's going to be a. So p is a pointer to an int. That's how we read it, kind of backwards. And then if you use star somewhere other than a type, like in an expression, star p equals star p plus 1, that is following the pointer. It's dereferencing it. Remember that? So that's c. The other one, address of, that's this thing. That's this idea. It's like you make an int x. You can make your pointer, int star p, hold the address of x like that. That's the ampersand. That's your address of operator. You see the difference? So there's just a lot of new things to keep in mind, and these are all overloaded things. Like you've seen the star before, you've seen the ampersand before in this class, but now we have new meanings for them. Okay? So yeah, where I want to go next is a magical place called the heap. It has to do with pointers, and it's a kind of global memory to a certain extent. So all right. We know one way right now to make variables that live forever. Those are global variables. We just make them outside of main. So like here's main, or any other function. Like here's main, and maybe we have other functions or methods. Like outside of any of that in the no man's land, we can make a global variable. We can say, all right, int global equals 42. And like that lives for the life of the program. That's fine. All right, so that's global variables. Remember that, hopefully. And who knows who's going to need this global variable, right? Maybe main needs it. Maybe some other function like half the way through your program needs it. Nobody knows ahead of time who's going to use this global variable. And so all this global memory needs to get created before your program even starts. Like global needs to exist before main even begins, because maybe main needs it. We don't know who needs this variable. So it's all going to get allocated. That's a new word. Allocation just means making in memory. So all global variables get made in memory, get allocated right as the program starts, and they last forever because anybody might ever try to access it, right? Because it's just around and visible to everyone. So they last until the program ends. That is sometimes not good because things live forever, because your global variables might live forever, that might ruin how much memory you use. Because like let's say you make a giant array as a global variable. That's going to take up a lot of memory. Add some zeros if that's not enough yet for you. But like that's a problem. Do you see it? Like that array is going to live around forever, even if you only needed that array for like the first half of the program or something. You didn't need it for the rest. Maybe you might run out of memory if you try to make too many local variables after that. You see the problem there? Like it's a waste of space to be using this array and keep it around for longer than you really need it. So this heap thing is going to solve that problem for us. All right. So to get there, we have to talk about like how memory gets made and how your program is arranged in memory when you start it up. So there are 4 different sections of your program when you load it into memory. So this is really what your program looks like every time you run it, any program that you ever make. It's got 4 different sections: text, globals, heap, and stack. All right. Those are the different parts of your program as it's loaded into memory. And let's think of it this way: like this is like lower addresses down here, smaller addresses, and then it's increasing into larger addresses down there. Okay, so that's like the arrangement of memory, the order of memory. Like text comes first. That's what I'm trying to say here. So the text section of your code of your program in memory is the machine code. It's the ones and zeros for your actual program. So it's like the machine code in your CPU understandable way of like your int main. It's like all your code is in memory somewhere in a way that the CPU can understand. All right, so that's the text section. The actual code of your program is there secretly, encoded in a way that the CPU can understand. And then there's another place just for the global variables because they need to live forever. Like the int that you made, the giant array that you made, who knows who needs it? So it's got to live forever. It'll be made right here. All right, that's a different section of memory. And then you have the stack, your function call stack. That's a place of memory that can change, right? Your stack starts at high addresses and it grows as things get called. It grows towards lower addresses, actually. It's a little weird. So the stack is growing towards lower addresses, and that's taking up a part of your memory. And like, it's going to take up some space, and then like it's going to be reclaimed as well when functions call and get returned. So here, like here's main. It's got some variables. Maybe main calls foo. It's got some variables. Then foo calls bar. So it makes some new space on the stack, right? For whatever bar needs. And then when bar returns, we come down to here again. So like the stack grows and shrinks. It's going to grow towards smaller addresses though, kind of backwards. And then there's this last place called the heap. The heap and the stack, they share this chunk. They share this chunk right after the global starts the heap. And the heap's growing this way, and the stack's growing this way. The heap is a place where you can ask for memory. All right. The heap holds a thing called dynamically allocated data. So it's just stuff that you want right now that you want to stick around. So like you can make an int on the heap, you can make a big long array on the heap, and the nice thing about this new thing called the heap is that you can get rid of memory as well. You can have it shrink too. So that's kind of nice. All right. So that's the new thing we're about to study. And the heap, though, can grow as well as the stack. So it can grow as you allocate more memory, as you ask for more arrays, more ints and things. The heap can grow. And you can, of course, call more functions, so the stack can grow. If ever these two things meet, the edge of the heap and the edge of the stack, because the heap's growing this way towards larger addresses and the stack's growing this way towards smaller addresses, they're sharing this spot. If they ever try to pass each other, then your program has run out of memory. I hope that makes sense, because like you can't call another function. You can't allocate another int or something. Like there's no room for those things anymore if they ever meet. So if they ever meet, then your program has run out of memory and you get a runtime error. All right, that's an unfortunate error to be getting. So hopefully don't allocate too much memory. Don't call too many functions. But that's what it looks like. That's secretly what's going on in memory. The stack grows down, the heap grows up. Maybe the drawing is a little backwards because of that, but at least the stack looks like how I've drawn it in class. So the heap is fighting for space with this thing called the stack, and on the heap you can ask for memory to get made for you, and you can also say, I'm done with this memory now, let me reuse it for other stuff. Just like stack memory can be reused for new function calls. So that's very powerful, very cool, and let's study it. So the heap is a place where you can have dynamically allocated stuff. So the memory that you make on the heap can live potentially forever if you ask it to, but you can also ask stuff to go away. All right. So unlike globals, any memory that you make on the heap can be removed. All right. And so you can make as much memory as you want. It doesn't have to be figured out ahead of time. Like you can ask these, or hey, tell me how many things you're about to give me. Store that into a variable or something. Like they could have typed 42, they could have typed a billion. And then you can go off and make an array on the heap of that particular size, however many things the user wanted just now. So you didn't have to know ahead of time before your program got run. Okay? How many things you needed to make on the heap? Like you can make that dynamically. It's very nice. And then you can say, I'm done with this now. Reclaim that memory. All right? So that's very, very powerful. And that's the kind of stuff that you can do on the heap. You can make memory and delete it, and it will live for as long as you ask it to until you're done with it. In between function calls, it's essentially a better global variable. It's global memory that you can kind of get rid of as well. So that's what the heap is good for. All right. So to make stuff on the heap, there's a new operator, and it happens to be called new. All right. So you say the word new, and it's going to give you back a pointer to some new thing that it makes for you on the heap. The only way you can access heap stuff is through pointers. And so that's why we had to learn about pointers first. So you say new, and then you say the name of the type that you would like to make on the heap for you. So you say, like, if you want an int on the heap, you'll say, I want a new int, please. And so it'll go off and it will make an int for you on the heap and give you back the address of where it got made. So it'll give you back a pointer to that int. All right, so here's kind of like, there's two sections of memory now. There's the stack, where you're making your local variables to like store stuff. Anything with a name lives on the stack. And then heap is a new place. It's like this line, int star n equals new int. Think about what's happening, right? You say, I want a new int on the heap. This line, this part of the line at least, will go off and create a brand new thing on the heap for you, a brand new box. Okay? It has an address. Let's say it's 100. And that's what that first part does. The new int part makes this brand new box on the heap for you, shiny and new. Okay? That's what's going to happen. It has an address. And what new int does is it both creates the box, then gives you back the address. It returns the address to you, which you can then shove into a local variable. It's got to be a pointer to an int, though, because it's going to give you back the address of where that int was. So then you can put in your n, like the address 100, and now you know where that thing is, where that box is, and you can set it just like a normal int, okay? So it's always going to give you back a pointer to that thing, and then you can set it to 42 or whatever. That's fine. This first line, though, it creates garbage still, as usual. It's uninitialized, it's garbage. You have to give it real values eventually. So there's 42. That's how you do that. Okay, so that's new int stuff. I think I'm not quite ready to show you what I want to do with that just yet. Yeah, the flip side is when you're done with heap memory, how do you get rid of it? There's a corresponding delete operator, all right? There's a corresponding delete operator. You say delete, and then you give the address somehow of something on the heap, all right? So, for example, if we had this set up, we had the 42, and let's say we're done with it now. We used it as long as we wanted to use it. Then we come along, we say delete n, and then it'll go to address 100, whatever's in n, and get rid of that memory. That's what that does for us. That's what the delete line does. We give the address, so that's n, that's the 100. That'll go here and delete that memory for us. And that will reclaim it. It's like a recycling service, and that will let the, like C++ use it, like it'll use this reclaimed memory for new ints if you ask for more stuff on the heap later, okay? So that's super nice. And so it's new and delete. There should always be a delete for every new. That's what I'm trying to say. So yeah, here's an example of the heap. So here we've got, let's be a little bit fancy. Let's start off, let's start small. So int star n equals new int. That makes the new int on the heap, so make space for one int on the heap and save the address of it into n. That's what that line does. That's this first part here. And it's set to garbage right now, but to change it, just like any other int pointer, we'll dereference and use that. So to give it an actual value, we'll say star n equals 42, and then we can use n all day long, like stout star n, del, stuff like that. There's my 42. So it's just a fancy way to print 42. And then once you're done using your pointer, you say delete. Delete that thing at that address, and it goes away. That's a good way of cleaning up, right? So once you're done with memory, make sure to delete it. And so nothing changes. We're being better programmers right now. Technically, when your program ends, all your memory goes away anyways, so you didn't really have to delete this if it's just like right at the end of the program you want to do that. But it's good practice. I highly encourage you to start this habit of just like every new, have a delete for it, okay? And so that's this example. We just completed that example. And it's kind of boring, right? You could have just used a normal int. Why do we need to go to the heap? Here's some of the cool stuff that you can do with heap memory. Like you can use it across function calls, and it's just like it's as good as a global variable, but you have more control and you can delete it when you want to. So here, let's make a new function. Let's call it make new int on the heap. And I'll give it a return type in a second. And here I'll take all of this and put it up here. So this is going to be interesting. So here, in this function call, it's going to make the int. And let's say I want to use that int that it makes on the heap in main too. It'll live there. It'll live forever. So what I can do is I can return n. See that? I can return that address of that thing on the heap, even though n itself is going away because it's a local variable. I'll be given back this address, and I can just keep using that address and call it something else. See that? So what does the return type then have to be? It's got to be int star. See it? Because I'm returning an int star. That's what n is. That makes a new int on the heap, and here I can be like, all right, int star p equals make new int on the heap. So this original function is going to use that thing for a second, makes it 42, prints it out, returns it, and now I've got that same address in p, and I can use it through p now. You see that? That's very powerful. So I'd be like, all right, star p equals star p plus 1, and mess with it through p. That's totally fine. So I can say cout star p you see the magic of this now? So now I've made like a global variable up here, and it lives for as long as I want it to, as long as I keep passing this address around. I've got a way of hooking into that heap memory. I can mess with it through P, and then once I'm done, I'll say delete as ever I need to. All right. So now it's called P though, down in main. So I hope you see the magic of it. So that's kind of interesting. You see how much power you can kind of have there. It's like a global variable. As long as you keep passing it around, you can keep using that heap memory, call it whatever you want. And once you're finally done with it, then you say delete somehow, all right, through that address. So that is a more interesting example, I think, a more useful example of how the heap works and how people like to use it. Like you just keep on passing it around and use that heap memory as long as you want. Cool. So that's that one. I next want to talk about arrays. So it's very odd, but an array is really a pointer. You may not have ever wanted to know that, but now you do. So when you make an array on, like, just on the stack, just a local array, it's just like this. When you say R by itself, actually, the name of your array, it's secretly a pointer to the beginning. So that's a little interesting. Okay, so let me draw what's happening. This is crazy. I couldn't tell you before, but now I can. So like there's your array. I've been drawing it like this, but that's secretly been a lie. R by itself, like let's say the starting address of your array is 100. Arrays are arranged, by the way, contiguously in memory. It's like if you have 100, if that's the starting address and it's an array of ints, the next int must be at address 104, because ints take up 4 bytes each. And arrays go in order in memory. Then the next element must be at address 108, all right? And then R by itself, if you just say its name, R, it's really a pointer to the start of that array. Pointer to 100. I will prove that to you right now. It's very odd, but there's a reason. Here, so int R equals 5, 6, 7. See out R. Oops. What is that? What is that about a pointer? And it's a pointer to the first element of R. So there's another way to get that, right? R of 0, give me the address of it. These are the same. And there's proof. That's so weird, right? So that means that, all right, another way to get to the 0th index of the array, because like this is a pointer to the 0th element, I could say star R. It's a pointer to the first thing. You better believe it. That is weird, isn't it? So that's a thing. So all right, let's mark this up. So R is the same as the address of the 0th thing, which means, because like if you think about it, the star and the ampersand are kind of like opposites of each other. They're inverses. They like it makes them go away, kind of, if you do them both. And so if you had that, if you had the address of the 0th thing and you said star on it, so star R then is R of 0. Because R by itself was this, then you said dereference that, which just meant follow the pointer, get to the thing. All right, so that might be a little complicated, but that's what's going on under the hood. R is a pointer to the first element. Very odd. Okay. Now you know. Okay, that's extra weird, but actually that's what the syntax is doing this whole time. It's doing pointer stuff. Crazy enough. Actually, let me show you what's happening. So if this is your array, so I've made the array 5, 6, 7. And just for ease of writing, let me say that this starts at address 10. That means this one must go at 14. This one must be at 18. Because they do go in order and they're ints. So that's my array. And I've called it R. And R is a pointer to the 0th element. It just so happens that this syntax is secretly doing what's called pointer arithmetic. So R of 1 is secretly like offsetting the address of R by 1 and then dereferencing that. All right, so that's called pointer arithmetic. If you add 1, if you say R plus 1, it will calculate a new address for you. All right, if you set r plus 1, it will calculate a new address, and it doesn't calculate if r is holding 10. It doesn't calculate the address 11. It's smart and it's nice to you. If r is a pointer to some ints, right, it's a pointer to an array of ints, that means the plus 1 then goes 1 int later, not 1 byte later, which is exactly what we want here. So r plus 1 will calculate the address 14 for you, actually, if that makes any sense at all. So that's an offset. That's pointer arithmetic. C++ will go based on the type of r, right? It'll go 1 int later, not just 1 byte later. Okay? And so yeah, this syntax is really just shorthand for this. It's really secretly translated to some pointer arithmetic to do some offsetting, and then a star. All right, so r of 0 is really like r plus 0, and then dereference it. Okay? That's interesting. So here, let me show that too. So instead of this, yeah, r of 1, what this is really being translated to under the hood is this. It's, all right, r, offset it by 1, go 1 int later, and then dereference it. See it? 2 6s. Crazy. Yep, so this is exactly equivalent to r of 1. It's what's being translated into, and so this is called, it's a fun name, it's called syntactic sugar for this. Because it's like, this is disgusting and nobody wants to learn that when they're first learning C++. So they made it this way first, and it's just like, it's candy, it's sweet, it's really a lie though. It's secretly being translated into this, all right? So yeah, now you know. That's very interesting. What else can we do with this? What else do I want to say? Yeah, you can do this for C strings, and actually, this is why you know, this is why like everybody says this, right? Char star instead of char bracket bracket. Because that's the same. An array of characters can be talked about through its starting address. You can say char star, that's fine. That's not an issue, all right? They are equivalent, that is okay. So, yeah. Now you know why people say char star to mean C string. It's like, this also means an array of strings. Or sorry, an array of characters, excuse me. Also means an array of characters, because you can just like store that, talk about it as its starting address, because that's what normal arrays are doing secretly anyways, all right? And then also, another cool thing that you get out of this is, you know, the char argv bracket bracket, that syntax for char star argv bracket bracket for your command line arguments. So this is the C string. It's an array of C strings. But what are C strings but arrays? Well, there's another way of writing this type if you wanted to do it this way. You could say char star star argv, and some people do it this way. That's equivalent, because this is just like any array is an address of its starting element, so it's just like a pointer to the first char star, to the first C string. That's what argv is. All right? That is wild, that is weird, and I just needed to tell you that now. All right? I assume it's a little confusing, but that's something you got to know. All right? That's why those are equivalent. And what does that give you? It does let you do some cool, interesting things. You can now use pointers to mean arrays if they really are arrays. You can say int star p equals r, and this makes total sense. And the types match, don't they? Because r is a pointer to the first element. It is an int star. You can shove that into an int star. That's fine. And then, even though it's an int star, you can use it like an array. That's okay. You can say go to p of index 2, because you know what that will do. It will take p, offset it by 2 ints, dereference it, and if it is an array, which it is, secretly, if it is an array, you can use it like one. That's totally fine. This is another way to get the last element. There's 7. Does that make sense? That's really odd, and I know that's a little confusing, so please yell at me with your questions. This is weird, but that is a thing. That is a thing. Now you can put arrays into pointers and use them like arrays if they really are, because you know it's going to really be translated out of the syntax. It's going to work. Okay? And yeah, I think that was most of what I wanted to show you there. That also bleeds into this idea of the heap as well. So you can make arrays and delete arrays on the heap like this. You need some extra syntax. You say new int still, but then you give brackets for how many elements of your array you would like on the heap. Okay? So that's what the syntax looks like. And you still get back this line right here will make a big long array of ints on the heap, and you still get back at the address of where that int array began. So you're still shoving it into an int star. You can't say like bracket bracket or anything. You must use ints. And that's okay, because we know that syntax works. So what this line does is on the stack and the heap, the following. So on the heap, this side runs first. So it says a new int of size 42. That'll make a brand new array of size 42. It's got a bunch of stuff. And here it is, shiny and new, made just for you. And it has a starting address, just like everything else. It has a starting address. What's the address of its first int? Let's pretend it's 100. All right. And then on the stack, we're going to save that into something with a name, into p. That's the address of where it begins. We get the 100 back from the new call. And so we have that set up. All right. And we can use p like an array. That's allowed. All right. It holds the starting address. We can use it like an array if it really is one, and it is. We'll be like p of 0 equals 42. Use it all day long. That's going to work with it just fine. Pass it around if we need to. And then the second you're done with your array on the heap, it's not just delete, because like it's an int star, but it's really an array. So like secretly, C++ doesn't really know the difference. It's like this could have been is this a single int that I'm pointing to on the heap, or is it an array of ints? You have to tell it. You have to tell it, no, this was an array, not a single int to delete. So you got to say delete bracket bracket to delete an array on the heap with a starting address. So that'll go in, that'll do this. All right, that delete line. So let's see, do I want to show you an example of that yet? Not yet, all right? Not quite. So here, I do have a question for you first, just to see if you're understanding things. This is a hard question, all right? Pause the video, try as hard as you can, all right? This is really gonna help solidify your knowledge. So here are 2 questions for you based on this code. So look at it, it's a little weird. Int star star p equals new int star, that's fine, this is a type. Star p equals new int, star star p equals 42. So those are 3 lines. Draw for me, please. Draw what's going to happen. Pause that video. Draw what's going to happen to memory. What's it going to look like on the stack and the heap? What's in each spot? All right. This is really going to tell you if you understand it or not. All right. So please give this a try. Draw what's going to happen in memory after these lines have been run, and then mark which one's on the heap and the stack. And then I would like you to draw what happens after you've done that. Draw what happens when you say the line delete p, because p is something. If you say delete p, what's gonna go away? Draw some X's. All right. Please give this a hard try, because it is a very good question to have you figure out what you know and what you don't know. All right. That will help you think of questions to ask me. So here, let me do it, assuming you've done it. All right. Shame on you if you've not tried it yet. Do pause the video. All right. I'm gonna assume you've done it though. So, all right. This first line, what does it do? So we say new int star. The right-hand side runs first. So it makes a brand new thing, brand new box on the heap of what type? Not an int, not a double, but an int star. So this box is capable of holding addresses of other ints. That's its type. It's an int star. All right. And we're shoving that into the correct type, aren't we? Because what does this give back? It gives back a pointer to that int star that it made for you. So its type must be an int star star. What new gives you back? It gives you back the address of that thing that it made for you. So we can shove that into something of that type. So p is something with a name, is living on the stack. Anything with a name lives on the stack. It's a local variable. Or a global variable if this is outside of anything. There's p. P's type is int star star. It's holding addresses of int stars, and that's exactly what we just gave it. Let's say that this box was at address 100. P is going to get that 100 and point just like that. So that's the first line. All right. Then we say star p equals new int. So star p is this, right? That box. Mess with that box. Set it to something. What are we putting in it? We're putting new int into it. All right. So what does this do? New int, just by itself, it's going to make a brand new box in memory that is capable of holding an int, isn't it? And then it gives back. What does new int give back? It gives back a pointer to where that thing got made on the heap. So it's really giving back an int star, which we can put into something that can hold an int star, which is star p. This box can hold an int star. Do you see it? That's what's going on. So let's say this is address 200. And so what that line does is it puts the 200 there in addition to making this box. So there's my pointer diagram. That's what's set up so far. All right. And that's supposed to be 200. I think I wrote it in a weird way. Let me rewrite it. That's supposed to be 200, just like that. You getting it? All right. And then star star p equals 42. What is that going to do? All right. Starting with p, one star gets you there. Another star gets you to here. So set that to 42. Bam. Just like that. So that's what the 3 lines do. Does that make sense? Ask me as many questions as you need to until this makes sense. This is a very good question. All right, so, all right, there's that. And all right, what happens now when delete P gets executed? I'll draw that in a different color. Let's say that we'll do this part in green. So when delete P happens, I'll draw in green what happens. Well, let me say what doesn't happen first. Delete P does not do that. You cannot delete a local variable. It just goes away when the scope goes away. You can never do that. You can only delete things on the heap. So that's not allowed. What does delete P do? It goes to this address and deletes the thing that was made there on the heap. So it goes to address 100 and it makes an X here. That's what delete P does. It does not delete this box. It does not go further and delete this address. That wouldn't have worked. You should have said delete star P would have done that one. Does that make sense? That's the only way to get this address 200 right now. Does that make sense? That's the secret. That's what's going on there. Delete P only deletes this one box right here. Okay? That's very, very important. And the second you do that, if you say delete P, because you didn't do anything with this box, it's just floating around. This box is just floating around. You have no way of getting to this box anymore. Does that make sense? You've lost this int. It is gone. There's no way to get to it anymore. You cannot go through deleted memory. It doesn't even make sense. It's not allowed. All right. So what we have just done, because this int is just floating around, we have no way of getting its address anymore. We just deleted the one thing that held its address. We have leaked memory. All right. That's called a memory leak. That's when you lost access to something, and that memory is just going to stick around forever. Like it's heap memory. It lives until you ask it to go away, and we have no way of guessing its address. It's gone. All right. So that's unfortunate. So here's another example of that. Let me draw this one. These 4 lines leak memory. So what's going on in this example? Stack and heap again. You have to be very careful now. It's a new kind of error. So this first line makes a new int on the heap. So it says new int, shiny new box. Ta-da! And it holds garbage right now, but it has an address. Let's say it's 100, and we're storing that address into the int star I. There's my I. And it holds 100 right now, and it points here. And we can mess with that box. Star equals 42, does that. And then we can say this, I equals new int. All right, so it's going to run the right side first. New int, what does that do? Makes a brand new box on the heap, has some address. It's shiny and new. All right, and then this gives back that address 200. We put that into I. So we just did that. And so now it's no longer pointing there, but it's pointing here. So that, here, let me draw what just happened in green. That line, this line right here does the following. It makes a brand new int on the heap with the address, of course, and it sets I to hold that address. It's just replacing it. So it's going to chop off this pointer. This is going to 200, which means it's now pointing to here. You see that? And then we can do the star I equals 43 on the next line. That's now setting this box. Do you see how we just lost the one way of accessing this one? This one's gone. We have lost its address. We cannot guess it. It's impossible to guess because your program's loaded into random places in memory. We have no way of getting this int anymore. It is going to be leaked. And so we've run out of like ways to get to it, which means we'll never get to it. All right, it's stuck. It's floating around. We'll never be able to use it. It is useless to us. So do your best to not leak any memory. And memory leaks are very unfortunate in programs that have memory leaks, that keep allocating things and keep losing those things that they allocate. Your program will eventually run out of memory because it keeps leaking, won't it? Whereas if you kept deleting your memory, cleaning up after yourself and reusing it, then it won't run out of memory. So memory leaks eventually lead to memory, like you running out of memory and your program crashing because of it. So that's very unfortunate. Okay, so with that in mind, just be careful. And I have an example of the heap now, all right, with arrays and like a useful example of the heap. So here's what we'll do. Let's ask the user for a number, and we will make an array of exactly that many things on the heap, let's say ints, and then we'll ask them for those n things. What do they want to fill the array with? All right, so we're going to make a heap array of that particular size. So we don't have to know up front. We'll just dynamically ask for the heap to make us that n many ints, please. And then we'll like use it. We'll like make it get the sum, and then we're done with the array, so we can delete it. All right. So here, let's do this. This will be a nice efficient example of the heap. This is more efficient than using vectors, by the way. I promise you that. So vectors was the other option for doing this, because you can't just make a normal array of some random size, because you're not sure how many things the user's going to want. So you can either use this heap or you can use vectors, and using the heap is more efficient. Oops. What do I want to do? I guess I want to call this... did I mess this up? There we go. So I want to call this array sum.cpp, and I did not say it right. There. So I want the user to give me how many things they want to type. So int n, how big do you want this array, user? And then I'll get that. And then let's make an array of that many things. Make an array of n ints on the heap. And so it's going to be int star r is the new int of that size. This gives me back the starting address of that array, so it's just an int star. Okay? And then let's put stuff in it. Let's ask the user for all those n values. Go to every index, ask the user for a value. Enter the next element. And put that into the right spot of the array. I could have done it this way. I could have just been like cn into r of I, but this is cleaner, I think. So there's that. So it's full, and then let's use it, right? Let's sum up the array. Let's use that heap memory for good. Sum everything. Make a sum variable, and go to every index. This is still a bit of a contrived example, but it's still useful. And we'll be like, all right, sum plus equals r of I. And yeah, then we want to output our sum, blah, blah, blah. That's most of the program, all right? But this is on the heap. We should always clean up after ourselves just in case we need to make more memory. So when are we done with this array is now the question. When in this program am I done with the array, with my array R? When do I not need it anymore? I totally need it for this loop, but to print sum, I don't need the array anymore, right? Its job is done. So I've already got the right answer. So done with R right here, in between. It's going to be delete bracket bracket to get rid of it. So you say delete bracket bracket if it's an array, then you give it starting address, which we're storing in R. Okay? And so that's the program. That's pretty much it. And yeah, the whole idea of using the heap is it's very efficient to just make a bunch of stuff at once. It's faster than vectors, because that would be your other option here. And now I could ask the user, like the fact that we deleted this means we've cleaned up after ourselves, we're not leaking anything. Now I could ask the user, even in a different function or something, I could ask the user for another array, and it would reuse the old thing, the old space, and reuse the first array's memory because it's been reclaimed. That's very powerful and very useful. All right, so that's quite nice. I hope that makes sense. So yeah, it's just a silly little simple example of using the heap to do something in the most efficient way possible. Vectors would be slightly less efficient than this. All right, and normal arrays are impossible because you'd have to do, if you were going to use a normal array, you'd have to like pick a size. Like, all right, you can't type more than 1,000 things, user. But maybe they wanted more. All right, so this is a good example to study. So there's the relevant code. Let's compile. Oh, did it say anything? No. Boop. So enter the array size. I don't know. Let's have it be size 5. 1, 2, 3, 4, 5. Those are my 5 elements, and apparently the sum's 15. But you can come around and do whatever size you want. Size 10, and it will just as easily make 10 things on the heap and ask me to type all 10 things into it. And it does the right sum there too. That's very useful, very efficient. It's honestly probably the best way to write this program. All right, using the heap. It's most efficient. So yeah, I think that's what I wanted to say for that example. I do want to tell you something secretly now. I guess it's not a secret anymore. Vectors and strings, C++ strings, are secretly using heap arrays, dynamically allocated arrays just like this. You make a vector of ints, it's really going to make an array of ints on the heap for you and potentially delete and resize it. Isn't that interesting? And strings are, of course, making arrays of characters on the heap for you. As you add more into it, like it'll potentially resize that that string and like have to copy it into a brand new place on the heap. But that's the secret. Now you know. All right. So like, there's a reason to learn this. Eventually, you're going to be asked to make your own version of vectors. Especially, that's like a very common CSCI 41 lab to give. I for sure give it. And yeah, now you know. So secretly, this stuff is happening, even though you weren't aware of it. All right. Now you know how to do it yourself. You could make your own vectors if you wanted to, with this kind of syntax, with these ideas. So okay, you may now be wondering, these are silly examples. Like I could have used vectors, just do it for me. I don't care. When do I really need pointers? Like when do I really need to make things with pointers myself? Because I am never going to, I'm just going to be lazy. I'm never going to use the heap for anything myself. I'll just use normal arrays all day long. I'm happy. All right. When am I going to be forced to use pointers and the heap and stuff like that? Here's your good answer. All right, it's called a linked list. It'll answer this question. When will I ever need to use a pointer over a reference? Like, I don't care. I'll just use references. I'll just use local variables. Like, when will I really need a pointer? When will I really need the heap? Linked lists are the answer. All right, this is a CSCI 41 topic. I will not test you on this. I will force you to read about it. All right. I'm going to force you to read about this thing called a linked list because it's the best example to give you right now of why you should care about using pointers and the heap, because there is no way other than using those to make this thing. Okay? So that's what I'm trying to say. And so I'm not going to teach you linked lists in full right now. It's a CSCI 41 topic. I'm just going to give you a sneak peek. I will force you to read about it though. It's one of the first things you hit hard in CSCI 41 though. All right? So look forward to that. But a linked list, it's a kind of data structure. It's a way of arranging data that has a bunch of things called nodes. And what those nodes do is they hold on to individual pieces of data. So each node has a single element of data as well as a pointer to the next node. So you're forced to use pointers, and all these nodes are usually made on the heap. All right. So what a linked list is, it's like a different way to hold a bunch of stuff in an order. So it's a competitor to arrays and vectors. Let me draw for you what a linked list is going to look like. So like the stack, like you give a name, like you give it a pointer for your starting element of your linked list, your starting node, and then all the nodes are made on the heap. So like, here's kind of what that looks like. Well, let me make the linked list that holds 1, 2, 3 in that order. So every node in a linked list looks like this. It has two things. The first thing is like a piece of data. So like that's where you can put your 1. And then the next thing is a pointer to another node in the list, to the next node. So you can do this. So then it's 1, then 2. 1, then 2, then 3. You make 3 nodes total. And then to mark, when you're done with the list, you put a pointer that like never works. A pointer that nobody can ever have access to. That's not a real node. So you'll put the 0 address there. That's null. And this is the linked list that holds 1, then 2, then 3. You're using pointers to get to the next nodes in your list. Does that make sense? That's a linked list. All right, you'll learn more about that, more than you can ever want to know in CSCI 41. Okay? This is a competitor to the array, right, or the vector that held 1, 2, 3. There are certain things that you can do much easier in a heap, or sorry, in a heap linked list than you could in an array. All right. For example, what if you wanted to add a value right here? In an array, you're absolutely out of luck. In a vector, you can only go and put stuff over here. Does that make sense? If you wanted to add something to the start of a vector, or if you had extra room over here in your array, you'd have to shift everything over. That's disgusting, especially if you have like a size 1 million array. You have to shift everything over so that now there's room to put your 0 there or whatever. With a linked list, look how easy it is. It's like, oh, 0, make the node, have the next pointer point to that. The start of the list is there now. Do you see how easy that is? That's insanely easy. Even if there was a million things in that list, there are some things you can do better, easier, faster with a linked list. Right? It's a competitor. There's some things that arrays can do better. It's fine. But it is a competitor. It's not the same. All right. So that's my example. Let me draw that out in full. So let's say that this is my setup. Let's say that I've got the following. I want to add a new element, a new node, to the beginning of a linked list. So you save on the stack, like a pointer to where your list starts. And here's the list. Let's say this is the list 1, 2. or no, let's do 1, 2, 3 again. 1, 2, and then 3 is the last thing in your list, and like null pointer we write like that. So this is the list 1, then 2, then 3. All right, it holds those values, and it's a competitor to this kind of array. 1, 2, 3. 1, 2, 3. And let's think about both ways. If I want to add a new value to the beginning of this array, I better pray that I have a room right here. First of all, you need that room ahead of time. And if you want to add a new element to the beginning of your array, you better shift everybody over. You see it? Shift everybody over. Make this 3, make this 2, make this 1. And now finally you have space here to put in your 0. And that would get disgustingly complicated if your array was huge. If you had 1,000,000 elements, you'd have to shift all 1,000,000 over. Do you see that? That's very unfortunate. Or all 999,999 to give you extra space. As long as you had extra space at the end, you have to shift everybody over, get the space where you wanted it to be. With a linked list, it's super simple. All right. All you got to do is, all right, here's my new node. Make it. It holds 0. And then set the next pointer to be like that. And then change where the list begins. All right. So this is what a list node looks like in memory. Here's how you make one. Struct. You say struct node. And every linked list node holds some data and a next pointer. So like int data. And then something called next. What is the type of next? It's a pointer to another node. So it's a node star. And this is a little weird. It's like you've got the type of the thing you're defining inside of itself. How does that work? Well, it's a little complicated, but that's called a recursive type, all right? And it's okay, it works out because you can eventually break the chain and like put it null in there. It's not actually a real node. So that's what linked lists look like. Each node looks like this. It's made up of data and a pointer to the next thing. And it's very, very simple to like add a brand new element. Add a new node, just make it on the heap, set the next pointer to the old first thing, and then change where the list starts. Change it to there. And now you can go through it in order. Whee! So that's super fast. See that? That's very nice. Some things that linked lists can't do is like go to the middle very easily. Like it's hard to get to the end. Hard to get to the middle for sure because you got to follow all those next pointers. That's one downside. But like the upside is you can put something at the start immediately. It's very quick. All right, so there's a trade-off for these things. But this is the best example of the heap and pointers. You are forced to use pointers. You're forced to use the heap with this thing called linked lists. All right, you'll learn more about this later, but I just wanted to show you now so that you're not like, I don't care about this. I'm just not going to remember anything. Now you know why you need to remember this stuff. All right, you're going to be forced to use pointers in the heap all day long in CSCI 41. Okay, so with that, I want to give you a wonderful, wonderful tool. All right, it's called GDB. It stands for the GNU Debugger. It's made by the people who made G++. This is going to help you debug your programs. It's great because everybody messes up, especially when we have to use complicated things like pointers in the heap and stuff like that. So GDB is going to save our lives, and let me show you how. All right, so GDB, it stands for the GNU Debugger. All right, it's short for that, just like G++ was short for the GNU C++ compiler. So these are just the people who made this stuff for free for us. It's very nice. It's just a program that can run your program in it. So GDB is another program. It's a debugger that lets you run your program inside of it, and it gives you helpful information about it. It's very nice. It'll tell you like the values of variables in between, even though you're not maybe printing them. It'll tell you line numbers where things happen, especially like errors. It's amazing. The only thing you need to do GDB, to use it, is to compile with one extra flag. It's called a flag. You say -G. All right? So -G, if you give that to G++ as you're compiling your stuff, it will add debugging information to your program. All right? So you say G++. And then instead of like your normal stuff, like foo.cpp-o-foo, you just add a -G right there, and that will allow you to run your program in GDB. Okay? So let me show you the magic of it. Let's make a program that like has a seg fault in it, and we'll discover the seg fault together in GDB. And so here, how do I want to make a seg fault? Let's make it be a little complicated, right? Let's be like, let's make a function called uh-oh. And we're going to call that from main, And let's have this happen in O. So int x equals 42, int star p equals null, and then we'll be like cout star p. So you see the error, I think, but let's pretend this was a more complicated program and you didn't see it immediately. This is going to happen to you in real life. So to compile, we're going to say g plus segfault, dash o segfault. And so you're going to get a segfault for sure. And now you want to use GDB because it's magical. It will tell you exactly what went wrong. So you're going to go back, you're going to recompile with a dash G if you didn't already. It'll still run when you do it that way. You can still run it normally. It'll still give you the segfault. But now you have the ability to run it in GDB. It'll give you helpful information. All right. So now we're ready. So to run it in GDB, so instead of saying the dot slash and running it, you just tack on GDB at the start. GDB is the name of the program, and then like give the program that you want to run inside of it as the second thing. So just like that, hit enter, and it will plop you into GDB. All right. My window is so large, it's telling me to press enter. It's just got to tell me a bunch of stuff at the start, but you might not see this because it might just spit it all out to you because your terminal might be larger than mine. But eventually, it gives you the prompt, and now we're inside of GDB, ready to run our program. All right? Watch. Now you say R for run, and it runs your program. I need to zoom out a little bit. It runs your program. It's like, all right, starting program, blah, blah, blah. And it's like program received, blah, 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 segmentation fault. And look at how nice it is right now. Do you see how this is going to save your life? All right, in the function on line 7 of this file, and I'll just print out that line for you for your reference. We got a seg fault. Do you see how amazing that is? It's going to save your life. It'll tell you exactly where the seg fault or other runtime error happened. It'll just stop the program right there. Isn't that beautiful? If that wasn't good enough already, you can say BT for backtrace. It will show you how you got to this function. BT shows you the stack. So here's the stack. So it's like, all right, maybe there's different ways to get from here, get to this place. It's like, all right, the way that you got here was main on line 11 called and then in you were on line 7. That's exactly the way that you got here. If that wasn't enough to show you how great GDB is and how you need to use it, you can also print the values of variables even though the program has just crashed. You can say whatever you want. Like, all right, you can print the values of your variable. Be like, all right, what are the values right now? I'm in my function. I can print x. Oh yeah, x is 42. That checks out. That seems fine. This line had a star p on it. What was p? What was print p? Oh no, that was the 0 address. I think I see the error. It could have been like print star p. It's like, oh, can't access that memory address. This is the greatest thing ever, guys. I cannot stress it enough. Do you see how amazing this is? GDB is the best thing ever. And so yeah, you can print out current things, and that shows you the variables value that's in your current stack frame. So like we're in right now, but you can move back out to main to see main's variables if you need to. There's a way to do that too. Even though the program is crashed, GDB is the best thing ever. All right. So once you've figured out like, okay, I understand what the problem is, let me get back to the terminal, you can say quit, or just Q to quit out of GDB. Quit. And it'll say like, I'm currently running your program. Do you want me to stop it? And usually like, yes, that's fine. Y for yes. Now you're back on the terminal. All right. GDB, best thing ever. All you need is the dash G, and then you have everything you could ever want, right? All the information that will help you solve your problem is the best thing. All right. So that's GDB in a nutshell. Please use it. It's going to help you. All right. And so that brings us to the end of our pointers slides. You learned a lot. I hope you can see the usefulness of a lot of the things. If nothing else, you can at least laugh at this joke now. All right. So if nothing else, you can enjoy that now. But yeah, that's pointers. And please ask me lots of questions. This is one of the hardest topics in the class. So it makes sense if you're confused right now, but I want to do my best to make sure you get it as fast as possible. All right. That's my job. So yeah, I hope to see you in office hours or something like that. And yeah, that's all I've got for you today.